It's the ultimate way to power the planet. It only has one problem, and that's we don't quite know how to do it. Why would you worry about a technology that's, 10 years away at this point? Because it's $1 trillion industry. Producing energy is about 10 trillion a year. And fusion might do 50% of that. Putting a bet on this is pretty serious. And then we found there was a whole raft of industries that depend on plasmas. And this is where we came up with the idea that we would do a plasma innovation center where the lab would help companies develop that technology. 46% of the steps to make a computer chip are made in plasmas. And one of the things that's exciting me the most is a different material. There's a need for somebody to start producing diamond at a quality level that natural diamonds don't even get to make quantum sensors, to make quantum computers, to make qubits, etc. AI is going to change the pace of discovery in science. And one of the subjects it's going to change is fusion. And I've spent my life trying to make fusion work, so it better happen before I die.
Welcome to Deep Tech Live by SOSV, the podcast where we explore the frontiers of deep tech and its impact on our world, with the help of top technologists, researchers, and pioneering founders shaping tomorrow. SOSV Deep Tech Live.
Thank you, everyone, for coming to this Deep Tech Live session. For those of you who have not been here before, these are somewhat impromptu sessions we do where we take leaders in certain fields and then we have a informal talk. It is broadcast, though, so we've got to watch what we say. My name is Duncan. I'm general partner here at SOSV. I look after HACS, which is the physical sciences side of what we do. It is an incredible pleasure and a true honor to have the only time I'm going to call you Sir Stephen Cowley here. Somebody who's been, really just an incredible influence in the fusion industry. You've been in it for many years. And so we're excited to talk a bit about your life's work and then some of the advancements in the sector. Thank you for joining.
Thank you for inviting me.
Before we start, I told my 7-year-old son that I was going to be interviewing a knight today. And he got very excited, but then also incredibly disappointed you were not coming to Brooklyn. So he has a bunch of questions for you. You feel free to come to our house anytime. We have a round table at our house. So he has all sorts of questions, not fusion related, unfortunately. But look, you started your career back in the early 80s. You first came to Princeton back then as a basketball player, and then turned to plasma physics. Was that a choice that you made yourself, or was that?
Well, I wasn't much of a basketball player, really. But at Princeton, I came to do a PhD. I'd grown up in Cambridge. My dad was a professor. I went to Oxford, and I played on the Oxford basketball team. Everybody was American on the team. They ended up doing very wonderful things with their lives, but we weren't that good at basketball, to be honest. And I wanted to do something different than my dad. So I applied to go to Princeton because I was interested in fusion. And one of the guys on the team said to me, "Don't go to Princeton. It's not a real American university." And I said, "What's a real American university?" And he said, "One where the football coach is paid more than the president." It's a pretty good definition, actually. And that's not Princeton, by the way.
Okay. And so now you're running the place. Can you tell? I mean, not the whole of Princeton.
I run the Princeton Plasma Physics Lab. It's one of the 17 national labs of the United States. And so I work in part for the Secretary of Energy, Chris Wright, and part for Princeton University, who runs it under contract to the Department of Energy. Yeah.
And tell us a bit about the journey up until that point. What has it taken you through?
Well, I like solving problems. I'm a theoretical physicist. And when I was coming through as an undergrad, my dad introduced me to fusion. You know how you are as a dad. I was a bit like this as a dad, but is that you're trying to find things you can talk to your kids to. And he's driving me to school, and I'm 15 years old, and he's a professor of engineering at Cambridge, and he's thinking of something he can talk to me about, and in the car, and so he tells me about fusion. And the idea that we could reproduce what goes on in the stars on Earth to make energy, that would be the ultimate way to make energy. Just took my imagination as a 15-year-old. And after that, even as an undergraduate, I said, this is what I want to do. And Princeton was the center of the world in that, and it still is the center of the world in that. I'd say that, wouldn't I? So I came to Princeton and loved every moment of it. I mean, grad school was great fun. Just you had nothing to do but think and try and try and do something that had an impact at that time. I got onto a really good problem. My second year in graduate school, we learned that the fusion reaction was dependent on the alignment of the spin of the particles. And the question was, could we keep them aligned? And I worked on that problem, and it was lovely because nobody had written on this problem at all. So I just had to sit and calculate, and my thesis advisor helped me calculate, and I got hooked. And on Sundays, I still calculate. But I'm a national lab director, so my basic job is to raise lots and lots of money to fund the lab. Yeah.
So if we just stand back and look at fusion as an industry, it's one that's had a lot of promise. It has a lot of optimism, particularly at the moment. I know you get asked this question a lot, but do you think that we're going to see a time, let's say in the next 20 years, where fusion has made its way into commercial reality?
So, there was a joke. I always tell this joke when I give a public lecture, because if I don't tell it, somebody will ask me a question at the end and tell that joke. And so I want to get there first, which is, the joke is that fusion is 30 years away and always will be. Because we've been trying to do it basically since the lab at Princeton was founded in 75 years ago in 1951. We've been trying to do fusion energy. And there's a simple reason. Once we know how to do fusion, pretty much we'll never not know how to do fusion. And there is millions of years of supply of fuel. It's the ultimate way to power the planet. It only has one problem, and that's we don't quite know how to do it, right? But in my lifetime, we've gone from to do fusion, what you got to do is create the conditions that are in the middle of a star. So it's got to get to like 100, 200 million degrees. And you've got to hold it at that temperature while it reacts like a star. And it takes isotopes of hydrogen and turns them into helium. And actually inside stars, it takes helium and turns them into carbon and makes all the things that are inside your body. I always say to students, you're just stardust. But we've actually been able to do that. And at Princeton in 1994, we did 10 megawatts of power out of one of our devices of fusion. Last year, the joint European tourists in the UK did 12 megawatts of power, but sustained for all of 5 seconds. So we're able to do it. The question is, can we do it commercially, right? And can we do it 24/7 in a power station and make electricity out of it? The National Academies in 2021 had a report that said, bringing fusion to the US grid, said that we should aim to get electricity from fusion in the second half of the 2030s. Which seems a long way off, but it's a lot less than 30 years. And the point is, we've got a lot of innovation to do to get there. Why would you worry about a technology that's, 10 years away at this point? Because it's $1 trillion industry, right? Producing energy is probably, if you look at the sum total of that industry, it's about 10 trillion a year. And fusion might do 50% of that. 5 trillion a year industry is a pretty big one. So, putting a bet on this is pretty serious. So what happened about 10 years ago is investments started to come into fusion startups. 9.7 billion in the last 5 years invested in fusion startups. Some big ones like Commonwealth Fusion that spun out of MIT. That's a 3 billion investment at this point. High net worth individuals seem to want an AI company, a space company, and a fusion company at this point.
And longevity.
And a what?
Longevity.
And longevity, yeah. Freeze their bodies so that they can see it. Yeah.
They can see it happen, yeah.
But I'm convinced of this kind of timescale now, right? We're not going to do fusion by 2028, although the startup that Sam Altman's invested in has said that they're going to deliver 50 megawatts to Microsoft in 2028. I'll be surprised. Okay. But I think we are going to see it in about a decade or so.
Have you got, I mean, just on the private versus public, have you got a view on a particular winner, one that's ahead in each of those areas?
I can't possibly say that here. no one is broadcast to the world. No.
Okay.
Look,
I mean, what about public versus private?
Look. There's something that's really happened in fusion research, and that is, in my lifetime, when I first got into this, we couldn't calculate anything. Right? Our computer models of what was going on inside our experiments didn't agree with the data at all. Right? In my lifetime, that's changed. And what has happened with that is a whole bunch of the early career people have started using the computer to find optimum configurations. And now, with the advent of AI models, they're putting together high-performance computing, AI models, and coming up with designs. And so, for instance, and I'm not advocating you invest in any company whatsoever, because I couldn't possibly do that, but there is a company, 𝐒𝐤 Energy, that spun out of our lab. It's in Newark, New Jersey. And they've come up with a computational design for a three-dimensional configuration that's never been tried. But on the computer, it looks like a fantastic configuration, right? So this is a different paradigm than it was when we came in. When I came into this world, people were imagining things and guessing things. We're now calculating things. And that's going to speed up innovation tremendously. What's happened in the Department of Energy in this last year is the Undersecretary for Energy, Dario Gil, used to be VP of Research at IBM. Dario has come in and he's launched an initiative called the Genesis Mission. And this is to bring more AI into science. You know that 2 years ago, the Nobel Prize in Chemistry was given for DeepMind to two people at DeepMind, one person at the University of Washington for the AlphaFold problem. I think he believes, and I believe, that AI is going to change the pace of discovery in science. And one of the subjects it's going to change is fusion. Right? We have a perfect problem for AI in that we don't quite know how to do fusion. We know how to do fusion, but not necessarily at a cost that the consumer wants to pay for their electricity. So we have to do a bunch of innovation to bring down the cost and scale of fusion. And having AI tell us, this is more promising than that, will reduce the development costs of fusion, I think, by a huge amount.
You mentioned in our prep that fusion's unlike fission. In fission, everything's kind of been done, but fusion is we're only probably 20% of the way there in terms of the ideas. Mm-hmm. What's the 80%? What are the other sectors that you think are important to fusion?
Well, there are two primary ways people want to do fusion. One of we at Princeton are sort of the world leaders in, and that's holding the fusion fuel in a magnetic field so that it can get to this temperature without touching the wall, right? And so you're making a magnetic bottle. So for that, you need very good electromagnets. And so a couple of the startup companies are developing high-temperature superconducting magnets. So they have a spin-out from, if they don't make it to fusion, they will have high-temperature superconducting magnets, for instance. The other way of, and so there's a slew of innovations like that. Because it's such a high-tech thing, it requires state-of-the-art technologies in superconductors, in steels, in vanadium alloys, in all kinds of areas like that. In the laser fusion, this is using a laser to compress the fusion fuel to make a little fusion bomb, basically, but it's the size of a peppercorn. So it's a thing the size of a peppercorn that gives off enough energy of about 5 or 6 hand grenades when it explodes. And they did this at the National Ignition Facility in 2022 and got net gain for the first time. Spectacular result. I mean, just a spectacular result. But to make that commercial, we've got to make more efficient lasers so that the lasers can get, you're not using, at this time, those lasers are about 1% efficient. So the electricity you put into the laser, only 1% comes out as light. So we've got to develop very highly efficient lasers, and there's lots of applications of highly efficient lasers. For instance, shooting down drones over El Paso turns out to be something you might want to do with an efficient laser. No comment, sorry.
We We've heard you talk about the importance on this topic of building out the fusion supply chain. And if fusion is so far away, I guess you're just saying that you're seeing so many technological advancements that are spurred by an ultimate goal of fusion, yet that have intermediate markets that are attractive.
Yeah, I think that's, any companies coming into this space have to look at, this has to be patient investment. And so a lot of the investment has come from extremely patient sources. I mean, high net worth individuals and things. Bill Gates, his breakthrough energy, has put a lot into the fusion companies, etc. But everybody would like to see some profit along the way into that. But look, if you solve the fusion problem, you're selling into an unbelievably large market, right? So ultimately, if you're successful in solving fusion, all the spin-offs will be negligible in comparison to what you earn from fusion.
Yeah. So it's a kind of a downside protection, I guess, for some of the other areas. Because, I mean, you talked about this acceleration of investment into fusion. That's certainly been even more true in the past couple of years. And a lot of that's been driven by interest from hyperscalers. Fusion doesn't meet their timescale, though. So what do you think's happening there?
Yeah, we had a conversation about this, and I have a particular view on this. So everybody's saying, we're going to need electricity for the scale up for AI, and there are 6 or maybe 7, big hyperscalers trying to dominate the AI market. It's existential for them. That's what they believe. It's clear, and you can name the companies, I can name the companies. And they've got to deliver in the next 5 years. And what they've got to deliver is good software and good data centers that can deliver fast on that in the next 5 years. So you don't have time for fusion to make a difference to whether you dominate the AI market. And what you can do, but a lot of these companies are very interested in sustainable development and not, increasing the amount of carbon that we put into the atmosphere. So for them, conventional nuclear is an option, and we're seeing that, with Microsoft, 3 Mile Island investment and the investment in small modular reactors. I think all of that is very positive. But of course, these companies are not looking just to dominate AI in the next 5 years. They're thinking 10 years, 15, 30 years down the road. And that's when fusion will come in. Fusion is the perfect energy source if we just knew how to do it, right?
You've been really bullish on the US's approach to supporting fusion. What do you think? I mean, and you mentioned the Genesis initiative there. But what other examples are there of initiatives that have maybe happened outside of our memory in recent times that have enabled the kind of the renaissance? I shouldn't call it renaissance. The interest or the progress that's happening right now within the US.
Well, I think. Definitely this breakthrough in actual being able to compute fusion. That's the intellectual investment. But we're being spurred on now. The China is spending, public sector spending in China on fusion is 3 to 4 times what the US is spending. We know China is very hungry for sustainable energy. It doesn't have many natural resources itself, etc. And fusion would really provide that. So they just introduced a big fusion technology center. They're building an intermediate device between the devices that we've just had and there's probably a fusion reactor. It's called BEST. I guess you can name an experiment. Calling it BEST is not a bad idea, but
what about hotter?
Yeah, hotter. Well, there's one in France called West.
Okay.
And the previous Chinese device was called East. So I think BEST is, but after BEST, what do you do? I don't know. But that's what they're building at the moment. And they're training about 500 graduate students a year. So there's a certain feeling in the US that this is not another industry that we'll let slip. Right. From our grasp. I mean, we do not want to be buying fusion reactors from another country.
Right. Yes. And then other efforts outside of the US and China? You're on the UK Atomic, or you were, sorry, the head of the UK Atomic Association. How would you summarize some of the efforts that have happened outside of the US and China, the two dominant forces there?
I think, well, the European fusion programs are very strong, and we are collaborating with them on the international machine that's being built in the south of France. Now, building an international experiment is both a sociological and a physics experiment. I mean, it's the cafeteria is very interesting, but the and that partnership, I think, has been very good. In fact, China has learnt from that, being part of that partnership, and the machine they're building is basically using technology that we developed for that. For instance, the niobium-tin superconducting magnets that we've developed for ITER, which is the device in France, is the technology that China's going to use for BEST. So they have a strong program there. But we particularly at Princeton have a strong link to the UK, and it's not me. It's that there's this concept of shrinking the device. The most common conventional device, called the tokamak, is the shape of a donut. And we found that if we shrunk the hole out of the middle of the donut and elongated it a bit like a cored apple, we could get much better performance out of it. And the UK has built one like that, and we're just about this year to put on a $400 million experiment at Princeton. The last piece came out of the mold in Bilbao, Spain last week. It's perfect. Thank God for that. All my fingers and toes have been crossed. And we'll be assembling that machine by the end of the year, and we'll be running with the UK team coming to us, and we'll be going to run on their machine, and this will be a joint program to develop that technology. And there are 5 startup companies looking at that technology. One in Japan, one in China, one is a UK startup company, and then one in the US.
You've mentioned quite a bit about AI being really creating a step change for the fusion industry. And part of that is around the ability to control or understand and how to control quickly the plasmas to create the effect that you want. Is that confined to fusion, or are there other applications that this could benefit outside of the fusion industry?
So, well, this is how we got involved.
Yeah, that's a leading question. For anyone who doesn't realize.
That was a planted question. So when I got back to Princeton in summer of 2018, I'd spent 9 years running the UK Atomic Energy, the UK Atomic Energy Authority. Sorry about that. I'm used to talking to students and yelling at them. So, if I yell at you, please forgive me. I got a call from a company in Korea, and they said, come out and talk to us. It's a microelectronics company, and the head of the company had worked at Princeton in the 1990s on plasmas. And 46% of the steps to make a computer chip are made in plasmas. Plasmas bombard the surface of the silicon. They cut trenches into the silicon. They deposit things in that, and then you put layer upon layer upon layer. And these days, a computer chip is completely three-dimensional. It started out sort of two-dimensional, and now it's sort of completely three-dimensional. And that process, called plasma processing, is the major process that goes on in the manufacturing of chips. And he had been in fusion, but he'd moved out of that and become head of research at this company. And he said, look, we're being challenged by China, and we have to make our chips better than the Chinese chips because they can make them cheaper. And part of the problem is that we're not producing enough. There are too many thrown away. You make a wafer of these chips, it's about the size of an old LP, and we have to throw away half that. And that technology was developed mostly actually in New Jersey at Bell Labs. The technology of the plasma processing has been developed largely empirically. You twiddle the knobs until you get a good chip. And then, if you get a good chip, that's fine, etc. But we're producing, the chips are more dense. They're more three-dimensional. Those trenches that you cut are 100 times deeper than they're wide, and you don't want them to wiggle around the place and all this kind of stuff. So we got into looking at how we could support this industry to understand what goes on in plasma manufacturing. And it turns out there's a lot of plasma processes in manufacturing, and they're all done in a semi-empirical way. So out of this bore the idea that we were really the place in the ecosystem of American research where we could apply real research methods to improving these things, right? Which is, we are now able to simulate that process, and we're able to simulate it and reproduce it and then have diagnostics inside the plasma tools. And we have this at several companies around the US that make the tools that make the chips. These are these plasma processing tools. We have little laser fluorescent devices inside there to measure the properties of the plasma, to know exactly whether it's doing what it's supposed to do and where it's doing and all that kind of stuff. The idea is to make, the chip processing more efficient, more precise, etc. And then we found there was a whole raft of industries that depend on plasmas. And this is where we came up with the idea that we would do a plasma innovation center where the lab would help companies develop that technology. This is the Plasma Forge, which we're doing with you guys.
Yes. What a great segue. So
it wasn't planted at all, of course.
So the Plasma Forge is a project which actually we'll discuss a bit more about that a little bit later. But essentially, it's like, okay, how do we create an environment where there are multiple industries that can get new innovation in plasma physics into their particular problem areas? And us as SOSV, as investors, we looked at this whole area. Initially, we'd thought fusion, and then we started to dig a bit deeper, and semiconductors suddenly came up as an interesting opportunity area. Why? Well, there's a number of reasons. So the US is now, in fact, there's a lot of sovereign investment into semiconductor supply chains because, you know what, people don't want to be sourcing all of their critical technologies from one little island that could, have a different leadership at some point. At the same time, the world of AI is going from data centers onto edge compute, physical AI. We're talking about it the whole time. We're trying to kind of discuss what it actually means, but it means basically compute and AI everywhere. And suddenly the types of demands that you have on a semiconductor become very, very different. And so beyond yield in semiconductor fabrication, which is what you're talking about there's also a whole range of other possibilities. Perhaps we could talk about some of those.
Yeah, I mean, look, if we can understand the process in a way that we can calculate it and we can manipulate it in our minds and on computers, we can do a lot better than just randomly twiddling knobs to get the best we can do. So it's about, different architectures on the chip. It's about the three-dimensionality getting bigger. But one of the things that's exciting me the most is a different material.
Right.
So about 4 or 5 years ago, one of the professors at Princeton came to us and said, there's a need for somebody to start producing diamond at a quality level that natural diamonds don't even get to, where the sort of flawless diamond, to make quantum sensors, to make quantum computers, to make qubits, etc. And the way industrial diamonds, element 6 is the industrial diamond part of De Beers, and we now have a collaboration with them, make diamonds, is in plasmas, and they lay down layers of diamond basically in the plasma, and the carbon atoms attach in the right way. And you don't want them to make graphite because graphite's cheap. You want to make diamond, and you lay this down, and you can make almost flawless diamonds with no dislocations, no flaws inside them, and then you can carefully dope them with things to make quantum sensors, etc. And Element 6 has been doing this for research purposes up till now, but they want us to sort of take over and take this to the next level. So we now have a row of these diamond manufacturers in the lab. And I think that the Plasma Forge is going to have diamond companies there.
Indeed.
It's a very interesting question, which I wish researchers can answer questions like this. At what price does diamond start to enter which market? Because obviously at the moment it's a lot more expensive than silicon, but it's a fantastic substance. I mean, it conducts heat like nobody's business. It has a wide band gap, which means you can use it in high-powered electronics. They're talking about doing things like putting a layer of diamond on next to the chip to just take the heat away, but only if it's cheap. Right. And there's no reason why diamond can't be cheap because it's made of carbon, right? Carbon's everywhere. It's just the structure. And if we can figure a way to bring down the cost of making diamonds to various levels, we will find it expands to bigger and bigger and bigger markets at this time. So we're investing some of DOE's money, but also private money is coming into the lab, and private money will be coming into the Plasma Forge to do this. I think it's a very interesting question. Yeah.
Yeah, I mean, this idea of going beyond silicon is something which is starting to get a lot of investor interest. There's diamond, there's gallium nitride, which is kind of more advanced, particularly used in power electronics. And then there's 2D materials, atomic layer deposition, like measured in atoms. And that's a critical area for transistor sizes to reduce down to actually improve or to keep up with the promise of Moore's law. Plasma is the enabling technology for that.
Yeah, we just got actually a microelectronics center out of the Department of Energy to look at the 2D microelectronics because there's a promise there of bringing down the power consumption incredibly. And because of data centers, etc., there's a big push to make the technology more and more efficient on the use of electricity. And, there's a sort of theme behind this is being able to put the atoms in exactly the right place. When you think of old-fashioned manufacturing, you put a drop of stuff on there and you planed the top off and sanded it down, right? Now we're actually carefully putting a single monolayer of atoms down in order to make some particular device. It's exquisite in the way that you can now manipulate at the scale of atoms.
Yeah. So I think we've covered off semiconductor materials. We've covered off some semiconductor processes. There's plenty of other ones, hybrid bonding, 3D stacking, etc. Another area that we got fascinated by was actually chemical catalysis. So it's a somewhat new field, but rather than thinking about thermal reactions to create the chemicals that really fuel the whole world, like ammonia, methanol, you can use plasma to do that as well. And there are some particular advantages around that. I was wondering if you could give us some of the things that you've seen in that sector.
Well, we've been looking at, and we did a lot of this during the Biden administration, looking at electromanufacturing. This is replacing processes that use fossil fuels with new processes which just use electricity because the electricity could be produced by fusion, it could be produced by renewables, etc. So it's taking fossil fuels out of the cycle of manufacturing as well as out of energy production. And in that area, ammonia production is a big one, right? That I'd like to do that too, but there's less interest in the present administration in that, but there's a huge interest in, for instance, critical minerals, and new ways to process and get critical minerals out of ores that are maybe not so efficient at this time. And plasmas can break the grain boundaries of the ores and break up the ores in a particular way that you're not just smashing the ore, you're actually exquisitely taking out the little bits of the little different substances that are within the ore in an efficient way. And so again, we're looking at a new initiative in the lab at plasma processing for critical minerals, and working with Princeton University in this, and etc. I think there's a whole bunch here because it's what you say in a plasma, because you've got an ionized gas. The electrons are being stripped off the atom. You've got this possibility of chemical reactions that don't happen except in a plasma. right? They just don't have a pathway in normal. And this way you can use those chemical reactions to do things that you couldn't in a normal chemistry do. This is precisely why we can make diamonds in a plasma, but you can't just sort of wash a surface with carbon. Yeah.
Obviously, fusion supply chain is going to be a big area. We've crossed off some of that. The last area for us is an unknown. 10% of a completely undefined opportunities. What would you hope to see in the? Sorry, I didn't ask you about this before, but what would you hope to see as some of the other areas that the Plasma Forge is looking at?
Oh, you sprung that on me.
We can move on if you want.
No, I think look. There's a general theme, I think, about what we've discussed, which is plasma physics was invented sort of in the 1950s. The fusion program in the 1950s was classified, and the lab at Princeton is the other side of Route 1 from Princeton, hidden behind the trees because it was a classified lab until 1958. And plasma physics was invented during that time. There wasn't really any theory, there wasn't any, etc. And so we weren't as far along as normal chemistry, etc. But in the last 2 decades, plasma physics has sort of got up to speed in its predictive capability, etc. So we have the industry surrounding it is suddenly getting this injection of capability that we didn't see before, where we were largely doing sort of Victorian type engineering, right? And so I think that what we're going to see, for instance, is gyrotrons. Mm-hmm. For instance, gyrotrons are devices that make high-powered microwaves, and we use them to heat plasmas for fusion. But right now, there's a huge interest in the US government and all around the world in gyrotrons because they make high-powered microwaves. And what we'd like to be able to do is to shoot down relatively slow-moving drones with something that's cheaper than a few $1 million missile. Right. And we could use microwaves to do that. So there's going to be a full court press over the next 2-3 years in bringing down the cost and bringing up the efficiency of generating, high-powered microwave beams. And that'll be good for fusion. Yeah. It might be good for the American military too. Yeah.
I mean, yeah, I feel like the military needs have been the defining force behind a lot of the advancements, certainly in the nuclear industry. And we talked about this a little bit before, but the Manhattan Project was, what was it? You had a very interesting quote around the economic effort there.
People can do extraordinary things in war. You only have to look at what's happening in Ukraine right now. What an inspiring thing to see people rise to the occasion of defending their country, right? And during the Manhattan Project, they constructed an industrial base for those 2 bombs that they dropped on Japan, Hiroshima and Nagasaki. The industrial base that they constructed was as big as the American automobile industry at the time.
Incredible.
And in 2 years. Right? I mean, just phenomenal kind of expansion and energy that was put into those industries at that time. Maybe we're seeing that energy going into AI right now. We're certainly seeing a lot of energy going into fusion right now. Yeah. And probably I'm wrong. Probably some of the early career people in fusion are saying, "Oh, he's saying again 2035. We're going to get it by 2030." So we'll see.
It does feel like AI is driving a lot of that kind of wartime effort around some of these initiatives. I want to talk a bit about kind of how some of these public-private partnerships have worked in the past. Like, the semiconductor industry, all of the very high tech, for example, ASML technology actually came out of national labs. There's been a lot of success. Also, there's been some lessons that we could learn. What are some of the important things that you think we need to bear in mind as we do this Plasma Forge project together?
So I'm very interested in this because, I started work, I ran these national labs in the UK, and we brought in an innovation centre at one of our labs there. And this was the first time national lab working with, innovation and incubation. So very eager to do this at Princeton too, and it's great to have SOSV as a partner in this. We've seen around the US wonderful examples of universities, faculty working with incubation and startups in order to power new industries, and it's the power behind Silicon Valley. It's around MIT. We have a burgeoning example of that in central New Jersey. But what we haven't seen up to quite recently is the national lab system doing this. National labs they're all modeled on Los Alamos, right? And the Manhattan Project. They were there for classified reasons at the start, and therefore there was no, we worked with big engineering companies, but we didn't worry about startups and innovation and things like that. There was innovation going on, but there was no thought into how do we make use of this crazy talent that's in the national lab system to help startups advance. And so one of the things we're hoping to do with the Plasma Forge, and you'll see that this is happening at Lawrence Berkeley Lab and other places, is the national labs are trying to make themselves useful as places, so we saw this in the Innovation Centre in the UK and on our lab. We had these companies that maybe had 2 technical people in them and, one admin and one CEO was raising money. And so 2 technical people, we had 400 engineers on our site. So we had a system whereby they, as part of their rent, they paid for something called the technology package. The technology package allowed them to call one of our offices and say, I have an engineering problem. I don't know how to solve it. Can I have an instant consultation with one of your engineers? And since we had 400 engineers, right, there's probably one of them who knew something about this, right? So, the two engineers in that company could talk to that engineer that afternoon and get an answer on it and move on, right? So there is ways in which this big concentration of talent in a national lab system ought to be able to help startups in a very immediate kind of way. And we're hoping this is something that will come out of the Plasma Forge. We're working with you on this, and yeah.
Okay, I'm going to ask you another question I didn't prep you for. If we had to do a pre-mortem, what goes wrong with this? If we're to think about like some of the areas that we want to make sure that we avoid, or some lessons learned from some of the other national labs attempts, either in the US or outside, are there any learnings there? One thing I think about is speed. Like the private, venture capitalists are very impatient people.
Are you?
Yeah, we talk about patient capital, but it's really not.
Yeah, look, the danger, and this is one of the things. It's a challenge for somebody like me who manages one of these labs. Is we've been around for 75 years working on the same problem, right? The sense of urgency may not quite be what you have in a startup.
Yeah, we've got 10-year life cycles on our funds.
Yeah, absolutely, and you should, right? Part of what the National Lab System does, for instance, is it a repository of expertise. And when you need that expertise, I once said, I was chairing a committee with the then director of Fermilab, which is one of the national labs outside Chicago. And we were joking around over a beer, and I said that high energy physics was really a thank you present for the atom bomb. And that the fusion program was a thank you present for the hydrogen bomb. And he said, no, you got it wrong. He said, what the government found out during the Manhattan Project, that having smart scientists at beck and call, and that when you needed them, you could tap them, was very, very important for your national security. They said, it's cheap to have a high-energy physics program to keep these people around. So Enrico Fermi stayed in the United States. Hans Bethe stayed in the United States after the Second World War because the United States invested in physics, that kind of thing. So we do provide that long-term sort of capability that when you need it for innovation or you need it for military things, it's there. So take, for instance, ASML, right, which is the company that makes the X-ray lithography devices for chips. That technology is technology that comes out of the nuclear weapons program. And it was developed at Lawrence Livermore Lab, and it's about directing X-rays, making X-rays and directing X-rays onto the chip so that you can make very fine-scale lithography on the chip. That capability was sort of lying around in the national lab system. It was there for the taking, as it were, if somebody just actually knew that that's what they wanted, right? And so I'm not so worried that we won't do something cool.
All right. I'm not worried about that.
I'd say that, wouldn't I?
Okay, then my last question then on this topic, as we're just getting to time. So, and this is definitely very, very self-serving, I apologize. But if we're to look 10 years ahead and think about, like, you could make one thing true about what we did together on this Plasma Forge project, what would it be and why?
I'm going to give two answers because I'm a politician, right?
Okay. And a question.
And I'll change the question, right? I think sociologically, I want to embed some of the values of the startup industry into our lab and have a relationship with the Plasma Forge and the lab that really does extract value from the lab and transfer that to innovate value for our country, for your country. Actually, maybe not you and me, but somebody else. Yeah. I hope the administration is not listening. But I'm a fusion nut, right? And we've got to get fusion to market as soon as possible. I think it's incredibly important to fill that hole of what's called firm energy in the energy supply chain. Renewables have come down in price. That's fantastic. I mean, wind is very cheap now. May not be as cheap as it used to be for various reasons, but wind is cheap, solar is cheap, and it's coming down, and we're going to be able to do that. But there is a real problem with renewables, is that energy storage is expensive, and the sun doesn't always shine, and the wind doesn't always blow, right? It turns out the worst month in Britain, I discovered this when I was working for the UK government, is December. And if you know anything about December in Britain, you know the sun doesn't shine. The other thing is that the wind actually doesn't blow in December very much. And all that offshore wind that they've installed in Britain does not produce very much energy during that time. So you've got to have something that operates in December, right? And fusion can do that for you. And it can do it without producing CO2 in the atmosphere, and it can do it without producing, radioactive waste. It can do it with, it really would be the perfect way to go. And I've spent my life trying to make fusion work, so it better happen before I die.
All right. Well, on that, I think we can draw an end to this Deep Tech Live session. Steve, thank you so much for joining us. Thanks to everyone who's in attendance and online. We will be still open for the next hour, so please feel free to grab a drink and grab Steve and ask him some more questions. Thanks.
SOSV Deep Tech Live.